Okay, it looks like everyone's in. So welcome everyone to this week's edition of Paleoperks. We're really excited to have Giovanne Mendes from the Universidade Estadual Paulista from Brazil. And Giovanne's talk will be about understanding the feeding habits of extinct caimans through empirical approaches, FEA and Gape Analysis. So a bit about the format of today's seminar, if you haven't been to a Paleoperk seminar before, or it's your first time here. So we'll have some welcome announcements for around 5 minutes, followed by Giovanne's talk, a moderated Q&A for 10 minutes, and tea time, which Giovanne has kindly agreed to stay around for. Don't forget to send your questions via the chat to the questions at Paleoperk's host, who today is Ahana. So a bit of housekeeping. So Paleoperks values the participation of everyone interested in the paleosciences. Please remember to abide by our code of conduct during today's seminar. If you somehow found yourself ill without having signed this, please take a moment to go to our website and review it. Please remember to mute yourself for the duration of the talk. You shouldn't be able to unmute yourself, but if you find that you can, please remember not to, so we can maintain a nice quiet environment for our speaker. You can ask questions by chatting to the questions at Paleoperk's host or by using the raise hand function. So if you do that, then we'll let you unmute and you'll be able to ask a question by voice. Any technical issues should also go to the questions host. We have closed captions built into our Zoom, and you can use the CC button at the bottom of your screen to show or hide these. Also remember to nominate all of your outstanding early career friends and colleagues using the form that will be in the chat very shortly. And remember to fill in our weekly feedback form, which is so that we know a bit more about who is attending our seminars. So this is anonymous, optional, and very much encouraged, and you'll be able to find it in the chat window very shortly. And now it's my great pleasure to introduce today's speaker, Giovanne Mendes. So Giovanne did a Bachelor's in Biological Sciences at the Universidade Federal de Finlandia in Brazil, followed by a Master's and PhD in Comparative Biology at the Universidade de São Paulo in Brazil, and is currently a postdoctoral fellow at the Universidade Estadual Paulista in Brazil, and undertaking an international internship period at the University of Birmingham in the UK. And with that, I will hand over to Giovanne for his talk.
All right, thank you. Is the presentation visible?
Yep, looks good.
All right, thank you. So first, thank you very much for the people, Paleoperks, for the invitation, and thank you all here that are here today to listen a little about fossil caimans and the paleoecology of fossil caimans from South America. So to start, we must first talk about the most diverse period of crocodiliforms in South America, in the Cenozoic of South America, which is the Myosin. And first, we have to talk about what is the Myosin. Well, as you know, the geological history of the Earth can be divided into two large periods, so as to say, which are the Precambrian and the Phanerozoic. And the Phanerozoic is divided between three eras: the Paleozoic, the Mesozoic, and the Cenozoic. That's how the history of Earth from 540 million years to now is divided. And within Cenozoic, Cenozoic is also divided in three periods, which is the Paleogene, the Neogene, and the Quaternary. And in the Neogene period, we have the Miocene epoch, which goes from 23 to 5 million years ago. And the Miocene is very important in South America because it is highly diverse. It has a very highly diverse fossil fauna of several taxa, including crocodilians. The Miocene is the epoch in which there is the largest diversity of fossil caimans and fossil crocodilians as a whole. So first, we have to talk about who are the caimans and who are the crocodilians, and we have to talk about then about what is an even larger clade with the crocodiliforms. So, as you know, we have this very large sauropsid amniote clade called Archosauria, which is the clade that has extant representatives as the crocodilians and the birds, but also many interesting fossil representatives like non-avian dinosaurs and heterosaurs, etc. And this group is divided between two, with Ave metatarsalia, the lineage of pterosaurs and dinosaurs, and the Pseudosuchia, which is the clade in which we have present-day crocodilians and all archosaurs closest to them, like ethosaurs. Within Pseudosuchia, we have several clades that lead to the extant crocodilians, like Crocodilomorpha, the first one of them, let's say, that originates in the late Triassic around 2200, 337 million years. And within Crocodilomorpha, we have Crocodiliforms, which originate also in the late Triassic, a little shortly after. And crocodiliforms are divided mainly between two large clades, which are Notosuchia and Neosuchia. Notosuchia is formed predominantly by forms of Gondwana, of the southern continents of the Earth, Gondwana, and predominantly by terrestrial forms, whereas Neosuchia, at least in the Mesozoic, is formed by predominantly forms from Laurasia, from the northern continents, and predominantly by aquatic forms. And within Neosuchia is the clade where we have Crocodilia, which is a crown group. So it's the clade that's formed by all extant crocodilians, all current species of crocodilians that we see today, and the most recent common ancestor and all of the descendants of this common ancestor. This is the crown group Crocodilia. And Crocodilia can be largely divided into three clades, each one the clade formed by those closest to a significant representative of the extant fauna. Those closest to the Aegean gharial form the clade Gavialoidea. Those closest to the Nile crocodile form the clade Crocodiloidea, and those closest to the American alligator form the clade Alligatoroidea. And it is within Alligatoroidea that we find the subject of today's talk, which is Caimanini. Alligatoroidea is divided between two groups. Those alligatoroids closest to the American alligator form the clade Alligatorini, and those closest to the caiman of the Amazon, Caiman crocodilus, form the clade Caimanini. So when talking about the crocodiliform fauna of the South America, in the Mesozoic, most of the crocodiliforms of South America were of the clade Notosuchia that I talked about you previously, and they were terrestrial. As most members of Notosuchia, you know the pattern for Gondwana. But in the Cenozoic, after the KPG extinction, there is an interesting faunal turnover in the whole world regarding crocodiliforms, but in South America also, in which most crocodiliforms are formed by Neosuchians. And within Neosuchians, we have Gyrosaurid, and we have other three clades. There are clades within Crocodilia, and these include Gavialoidea, Crocodiloidea, and Caimanini. The only clade of Notosuchia that survives into the Cenozoic in South America and in the world is Sebeside. So, talking now briefly about each of these clades. So, Sebeside is the only Notosuchians that inhabit South America in the Cenozoic. They become extinct in the Miocene, and they were basically terrestrial predators, like the Notosuchians before then in the Mesozoic. They were large, medium to large-sized taxa, with the exception of Lorosuchus that you see in the upper left over here, which was an aquatic taxa, but most of Sebestides were terrestrial predators. Other group in the South American Cenozoic is Girosauridae, which is a Neosuchian. They exist in South America until the Paleocene, but they went extinct in the whole world by the Eocene. And Girosauridae is very interesting because in the world as a whole, Girosauridae is mainly a saltwater taxa, an oceanic taxa, but in South America, most of the forms are freshwater. We have also marine gyrosaurids like Guarinisucus that you see over here, but most of South American gyrosaurids are freshwater taxa, like the ones you see over here, Serregionisucus, Acherontissucus, and Anthracosucus. And Anthracosucus is also very interesting because it differs from most gyrosaurids, which are longirostrine taxa, have a long rostrum and presumably piscivorous forms. Anthracosucus has a wide rostrum that indicates that he had different feeding habits. We also have Gavialoidia in South America. We don't have them anymore. They are only in India or maybe in Malaysia if Tomistoma is agareo. But Gavialoidia was present in South America until the Miocene. The first appearance is either in the Cretaceous or in the Oligocene-Miocene transition. This is not clear yet. And Gavialoids of South America were pretty much like the India gharial of today, but some of them are very large. Gryposuchus could reach, in estimations, to 10 meters in length. And Gavialoids are divided between freshwater and saltwater forms. There are freshwater forms like Gryposuchus and Sperogavialis, but also saltwater forms like Siquesuchus and Piscogavialis. The crocodiloids of South America can be divided between two groups. One of them is Thomistomines, the group closest to the extant Thomistoma, the extant Malaysian gharial, and the other is the genus Crocodilus, which exists in the continent until today. Here we see both of them. We have a crocodiloid in South America until the Miocene. We have Thomistomines like Aractosuchus, and from the Pliocene to this day, we have the genus Crocodilus, Crocodilus falconensis, that you see down left was the first fossil occurrence of Crocodilus, and we have this genus, of course, until today in the continent, Crocodilus acutus and also Crocodilus intermedius. And then we have the group that we're going to talk mainly in today's talk, which is Caimanini, the caimans. Caimans have 6 species, current species within 3 genera, Caiman, Melanosuchus, and Paleosuchus. And the interesting thing about caimaninis in South America is not only that they are a very diverse group taxonomically, but they are also a very diverse group ecologically. We can have at least 4 different ecomorphotypes between fossil caimans in the Cenozoic of South America, which are those are generalist predators, like those who exist today, the giant predators, which is Purosaurus, the Durophagus taxa, those specialized in hard-bodied prey, small hard-bodied prey, but of hard bodies like mollusks, insects, etc. And Morasuchus, which is traditionally recognized as a gulp feeder, as an animal that might capture its prey, like using the lower part of its rostrum as a fishing net instead of being an active predator. So the fossil history caiman in the beginning, in the Paleogene, in the beginning of Cenozoic, is actually very poor. There is not many fossils, and those are largely incomplete. Those you see over here are some of the most complete fossils of caiman in the Paleogene. But when you get to the Miocene, as I was talking before, the diversity of fossil caimans becomes extremely large and extremely significant. To start, in Caimanini, in the Miocene, we already have representatives of the extant genera. We have representatives of caiman, of Melanosuchus, and possibly of Paleosuchus, even though the assignment of this fossil over here to Paleosuchus has been questioned. But anyway, we have representatives of the current genera already in the Miocene. But we also have a very large fossil diversity, and this fossil diversity, I will approach it here regarding its ecological aspect, its different ecomorphotypes. So in the Miocene of South America, we have generalist caimans, that could eat anything but were from small to medium-sized taxa, which is, among others, Acresuchus, Paranasuchus gasparini, and Melanosuchus caiman, most caimans, and Paleosuchus, as I talked in the previous slide. But we also have, of course, many Durophagus forms, and these ones were proposed to be specialized in its hard-bodied prey, small hard-bodied prey like mollusks, crustaceans, and insects. And these adaptations to consume this hard-bodied prey would be the large globular teeth that, as you see in Caiman langstoni and Gnatosuchus over here, which would be useful to crush the prey. The short rostra which would give larger strength to crush this prey as well, and robust mandibles for the same objective. So there are many possible adaptations for this specialized diet. And the Gnatosuchus that you see down right is especially interesting because its mandible is modified like it was like a shovel, if you like, adapted to grasp through the bottom of the rivers and lakes or the margins in search of these mollusks or of this hard-bodied prey. Then we have also Purosaurus, which of course it's one of the largest fossil crocodiliforms of all time, with maximum estimations between 8 and 12.5 meters in length. And Purosaurus has been traditionally considered as an ecomorphotype of its own because of its large size. Not many studies have been carried out on its diet habits, but of course, its large size is outstanding in its own right, and of course, it merits further research, detailed research into its feeding habits. And of course, we have Morasuchus, which is the most different taxa from the Miocene of South America. It had a very long, wide, and flattened rostrum, as you see in the pictures, which is very different from most crocodiliforms. There are some in the Cretaceous of Northern Africa, like Stomatosuchus, that are alike it, but they're not related. And the feeding habits of Morasuchus have been puzzling the crocodilian community for quite a few time. The most traditional or the most talked hypothesis is that it was not an active predator because it had small teeth. It has a lot of teeth, but they are very small. And of course, this rostrum, this wide, long rostrum, the hypothesis is that it could be used as a fishing net, as some sort of fishing net, more or less like a pelican. So it would capture prey, presumably small or in large quantities, small prey, with the inferior part of its rostrum, like it was a fishing net or a gular sac, and then consume it more or less like a pelican. But obviously no empirical assessments had been done on this issue until now. So then we have the extant caiman diversity in South America, which comprises of 8 species and 3 genera. The crocodile diversity is 8 species and 3 genera, being 60 species of caimans and 3 general caimans, and 1 Crocodilius genus of Crocodiloidea, with crocodilos. But of course, the caiman diversity may be much larger because recent genetic studies are pointing to cryptic species that can be proposed or distinguished in the near future. But even then, it's important to note that all of these species that inhabit South America today are small to medium-sized generalist predators. So the Miocene caiman fauna of South America was much more diverse, both taxonomically and ecologically. And despite this giant diversity and this interesting diversity, which is comprised by these four ecomorphotypes, as I told you before, the generalist predators, the giant predators, Purosaurus, the gulp feeder Morasuchus, and the Durophagus taxa. The fact is that nearly no empirical assessments on the paleoecology of Caimanini have been carried out to this day. Most studies on the subjects have been largely theoretical and speculative on how these animals would feed themselves and what kind of prey they would capture, etc. One empirical study was a bite force estimation for Purosaurus from 2015 that resulted in an estimation of 69,000 newtons based on regression equations. But aside from that, no real empirical studies had been carried out. And it was in order to fill this void that we had decided to propose my current postdoctoral project, which is exactly an assessment, an empirical assessment on the paleoecology of these fossil caimanines of these four ecomorphotypes. And we decided to do this through several techniques actually, but one of them is finite element analysis. Finite element analysis, to summarize, is a technique that allows you, if you have a virtual model, a CT scan model of a fossil taxa of the skull or the mandible, for example, allows you to transform this model into the model of a solid and using the properties of this virtual solid to make a lot of experiments, a lot of analysis to test these physical properties of the solid, like resistance to stress, for example, and among many others. But for biological organisms such as crocodilians, one interesting application of finite element analysis is the estimation of bite force. So you obtain a model of these fossil crocodilians through CT scans, transform this into the virtual model of a solid, and through this, you can make estimations of bite force in newtons. Another technique that we are using is the Gape analysis. The Gape analysis also uses virtual models of CT scans of skulls of taxa. And once you model the muscles involved in the opening of the mandible, which are these cylinders you can see over here, these colored cylinders you see over here, you can make a simulation, an analysis that will give you the angle of the maximum opening angle of the opening of the mouth in that taxa. And this is the tool to evaluate feeding behavior. It allows you to determine how much this crocodile could open its mouth, and allows you to make inferences about its diet and its methods of capture or prey, which is exactly to the questions we seek to answer. So then we established this project, which is to understand the paleoecology of caimanines of the Miocene of South America through empirical analysis, especially through finite element analysis and Gape analysis on these four ecomorphotypes. So the analyzed taxa were specifically among the generalists Acresuchus, among the Durophagus Caiman brevihostris, among the giant predators Purosaurus, which is the only one, and among the Gulf feeders Mourasucus, which is also the only one. All of them from the Solimões Formation from the late Miocene of Brazil. And we also made some analysis based on models of specimens of the extant caimans, caiman latirosses, and Melanosuchus liger to compare with those of the fossil taxa. So the first step of the project was to make CT scans of the specimens of interest, both fossil and extant, as you see here. Sorry. The second step was the estimations of bite force, which are due to finite element analysis. These bite force estimations are done through the simulation from the modeling of the muscles involved in the bite movements of this taxa. This modeling is done by understanding the surface areas of the muscles in the real specimens, in the actual specimen, and modeling them in the virtual models through these arrows you see over here. These arrows will comprehend the whole area in which the surfaces of the muscles attach, and the surfaces of the muscles, as we calculate the area of the surfaces of the muscles in the actual specimens as well. And through these calculations of the surface area, we can know the amount of force that these muscles employed. So both the surface and the force that these muscles employed are important to reach the final number of the bite force estimations. So, and then in the bite force estimations, we get partial results. The bite force of Acresuchus, the generalist, was estimated in 419 newtons, and the bite force of Caiman brevihorsis in 459 newtons. It's a little bit larger. These images over here show the distributions of the stress, of von Mises stress among the mandibles during the analysis, which are data that we're going to use in future analysis. The bite force of Mourasucus was around 500 newtons, which is just a little bit higher than Acresuchus and Caiman brevihorsis, which is an important information. And the bite force of Purosaurus is approximately 16,500 newtons, which is higher than all values estimated for extant crocodilians by the work of Erickson in 2012, in which he directly measured the bite force of extant crocodilians. He made individuals of extant crocodilians bite into a surface and measured it. But it's interesting that the single largest bite force they measured is only a little lower than our bite force estimation for Purosaurus. But even then, the bite force of Purosaurus is quite big. And the bite forces of Melanosuchus and caiman, which are the extant taxa, were also a little bit slower than a little bit lower than the measurements of Erickson et al. Based on direct measurements of living individuals. In the case of Caimans our estimations was significantly lower, 105 newtons, but that can be explained by the fact that the specimen that was available to us was a juvenile specimen. But these results, as well as the Purosaurus results, may indicate that muscle modeling may be underestimating bite forces. And this is a perspective that we will examine in the rest of the project from now on. But interesting results came from the Gape analysis. I'm not going to reveal the exact number because these data are unpublished. But the fact is that caiman brevihorsis has the smallest gape angle opening. There's the smallest mouth opening angle between all analyzed taxa. whereas Acresuchus has a median value between the taxa, similar to Purosaurus. Exactly, Purosaurus is similar to Acresuchus, but the gape opening of Morasuchus is the largest between all taxa. So what all these results reveal altogether when considered uh, all of them in conjoint. So these results for Caimán brevihostris, they are very interesting because they indicate that really it was a Durophagus taxa for two reasons. First, it has the lower gape angle of all of them, so it indicates that it ate small prey. After all, it could not open its mouth very much. But also, another factor that shows that it could be Durophagus is that its bite force is larger than Acresuchus, even though Caimán brevihostris is smaller. And these larger forces may be necessary for it to crush its hard-bodied prey. So both the gape angle and the bite force indicates that Caimán brevihostris was a Durophagus taxa, and they indicate that Acresuchus was a generalistic taxa. It had a median gape angle to capture both small and larger prey, and it had a bite force smaller than Caimán brevihostris because maybe it didn't need to be so strong. Morasuchus is very interesting because its bite force is practically similar to Caimán brevihostris and Acresuchus. Even though Morasuchus is much larger, Morasuchus can reach to 6-7 meters, whereas Caimán brevihostris and Acresuchus in maximum 2 to 4 meters. So these corroborate long-held views that Morasuchus had a weak bite force. But the most interesting thing is that Morasuchus has the largest gape angle of all taxa, and this corroborates the idea that could use the inferior part of its rostrum as a fishing net. After all, it could open its mouth much more than all the others, so it could use the inferior part of its rostrum as a fishing net. And Purosaurus, well, of course, its bite force is significantly larger than all the others because it's a very large taxon. But its gape angle, the opening of its mouth, is not very different from Acresuchus, and this indicates that Acresuchus is some sort of a generalist taxa of large size. So, of course, it could capture large prey, but it's due to its large size alone by itself, and not exactly because there's something special about its gape angle, but of course its bite force is much large. Ongoing developments and perspectives that we have in our project is also the performance of a morphospace analysis based on geometrical morphometrics to determine quantitatively how different these taxa were regarding their ecology through the morphospace analysis based on characteristics of its mandible. We also aim to make gape analysis in extant taxa, Caimán, Latihostris, and Melanosuchus niger, to compare with the extinct taxa, and also an evaluation on whether muscle modeling could be underestimating the bite force on fossil taxa. So I'd like to thank everybody, thank the Paleoparks for the invitation and the opportunity, and thank my supervisor in Brazil, Professor Felipe Montefeltro, and my supervisor in the UK, Professor Stefan Lautenschlager, and FAPESP, and everybody for being here and listening. These are my social media and email. Thank you.
Great. Thank you so much for such a fantastic talk. Just a quick reminder to the audience, you can send in your questions via the chat to the questions at Paleoparks host, or you can raise your hand and we will unmute you. So we've had a few questions in already. First one we've had is, How did the Paleocene-Miocene thermal maximum affect the crocodilian turnover from Notosuchians into Neosuchians? Did it help Neosuchians acclimatize to the South American ecosystems?
Well, the turnover from Notosuchians into Neosuchians has more to do with the KPG extinction itself, because when that happens, the only Notosuchian clade that survived in South America was Sebecids. All the others went extinct, and then, so I should say, South America was reoccupied by Neosuchians then. And of course, that happens all over the world. You know, Sebecids were not only the only Notosuchian clade in South America, but in the whole world. But I think the Paleocene thermal maximum really helped this Neosuchian fauna, because of course crocodilians are more adapted to hotter environments, so it helped them to thrive in the Paleocene and Eocene and reoccupy South America. So it happened in that sense, but you have to reoccupy the continent. But I believe the end of the Paleocene-Eocene thermal maximum may have had an effect on gyrosaurids, because it may have been responsible for its extinction in South America at the end of Paleocene, and a lot of people also believe that gyrosaurids went extinct in the Eocene when the global temperatures dropped. I don't know now if this is exactly the same event at the end of the Paleocene thermal maximum, but the global drop in temperature has been uh, estimated to be the reason why gyrosaurids went extinct.
Great, thank you. Another question. What's the biggest challenge of undertaking finite element analysis on your samples? How does preservation affect your data?
Well, yeah, working with fossils, it's always a challenge on the preservation issue, and obviously we have to choose the best specimens when they are available, but they are not always available. So one solution that we had is that we have been modeling, for example, parts of the fossils that were not preserved, and we are creating new models from these parts, for example, teeth and other parts that are missing. But only when they're necessary, it's strictly necessary for the analysis, not doing anything for aesthetical reasons, if you like. But for example, indefinite element analysis of crocodilians for bite force estimations. The fourth mandibular tooth is very important because it's the tooth where the bite force is better estimated. And so to have the tooth is very important. So when a specimen doesn't have it, we put a tooth over there. But it doesn't affect the results, and it actually gives you results. So yes, finite element analysis preservation can definitely be a problem, but it's a problem that you can resolve. Not always, of course, but you can find alternatives.
Nice, thank you. So we have another question. Which fossil find has been the best experience for you until now?
Well, I haven't had that much of field work experience, but I think when I was in a field work in Acre, the same place where these fossils came, once we found two turtles, I believe from the Calus genus, which they were together, basically, and it was very difficult to take them out of the rock. It was a lot of hard work, but we did, and I think that was the most interesting find. And in the same field work, we also find an odd another turtle, which was Podocnemidid, and but we could not take it out of the rock because it was very deep into the forest. It would be like a whole expedition just to take it out. But it was an interesting adventure to go deep into the Amazon rainforest for the turtle.
Awesome. So we have another question. So were the different members of Caimani, which occupied similar feeding niches, closely related to each other? Were all the Durophagus caimans closely related to each other, or was selective pressure strong enough to push for convergent evolution?
All right. So according to the recent phenologies, you have at least some different groups, some different lineages converging into this Durophagus habit, because Gnatosuchus, that one I talked about, that has this shovel mandible, and another taxon called Globidentosuchus are usually recorded as early divergent caimans, very in the beginning of the radiation. Whereas taxons such as caimans, Caiman wallingstoni and Caiman brevihostris that I'm studying, they are close to Cayman. They are close to the most recent uh, Caymanins. So we have then at least two. But we have other taxa. There is Kutana Caiman that was in the presentation as well. We don't really know where it fits in the phylogenetic tree so far. So yes, my best guess is that yes, it will be a case of convergent evolution. I don't think they are all related to each other. You have at least two different groups. One is most early diverging group, and the one this more derived group. But of course, there's still a lot to be done in the Caimanini phylogeny as well.
Great, thank you. So I seem to have a bit of a lull in questions. See if there's any more that come into us. We'll give it 10 more seconds to see if we get any more questions.
Mm-hmm.
Okay, well, looks like we've come to the end. So I will take back the screen share from you.
All right.
Great. So thank you very much again to Giovanni for such an awesome talk. I know I learned quite a lot about your species. This is outside of my area of expertise, but thank you. So thank you very much again to all of the audience for joining us. Please remember to fill in our weekly feedback form so that we can learn a bit more about who attended today's seminar, and join us next week on September 24th for a paleobiology themed talk by Cecily Eccles from University College London in the United Kingdom. And up next, we have tea time with Giovanni. So this is an informal conversation about the talk in a relaxed setting. So we very much encourage you to stick around for this. And our question of the week this week is, if you could live in any paleo environment, which one would it be and why? But first, it's time for a quick break before tea time. So remember to get up, walk around, and have a quick drink of water. Come back in 2 minutes, and if you have pets, please bring them to tea time as well. We always like to say hi. So we will see you in 2 minutes.